Alright, so in the previous class we talked about the linear system, linear equations, Ohm's law, and the quantities and the circuits in which it appears. So here we talk about these signals. Signal is a physical quantities, and these are the real quantities. These are the quantities in the real world. So what are these physical quantities out of which we can get the signal? Is that we have a temperature, is a sound or audio, we have video, we have pressure, is the air, touch, motion, etc. So there are many physical quantities that exist in the world, and usually what we need is a device is called as transducer. So that converts this physical quantities, output from the physical quantities, into a valuable output electrical signal. So that's the function of transducer. So it's like we have physical quantity and it converts into a transducer, give its output in the form of electrical signal right over here. And usually it is a sine wave or a square wave or any other wave function that we can measure by means of electronic equipments in the laboratory. So and there are other ways to generate the signal. Is the signal source. So as you can see here, what we have is a signal source, as you can see here. So there is a voltage source represented by Vs of t, and it has a source resistance represented by Rs. Okay, and this is this is the voltage signal source right in the left, and on the right side we have this current signal source, where the current source is given by Is of t, and it has a resistance in parallel represented by Rs. So if it is ideal voltage source or ideal current source, what we can write in ideal case, Rs is equal to 0 in the case of voltage source. So it is just a voltage source connected, and Rs would not be connected over in this circuit. For the for the ideal current source, it would only be Is of t as represented by this current source, because in that case Rs tends to be infinity. So it's we can open this circuit right over here. So since ideal situation doesn't exist in practice, so we call them as a practical sources, practical signal sources. So to the left we have a practical voltage source, and to the right we have practical current source. And to the left, this is usually called as Thevenin's form, is a Thevenin's theorem, and on the right we call it as a Norton's form. So the way we can represent a current source, so it's in the Norton's, it can be derived from the Norton's theorem. So that's not our objective to derive these theorems in this lecture, and these two forms can be represented by this equation right over here. So in any circuit, to the left or right, the figures that we see here, we can write the expression like this: Vs of t is equal to Is of t into Rs. So it's like voltage equals current times resistance. So again the Ohm's law. So that is how we can represent the current and voltage signal sources right here. So the question here is, in the left side of the figure, what is given is there is a voltage source Vs of t. It has a resistance Rs right here, and a load is connected across this signal source, and that load has a value of resistance RL, and we are asked to determine the voltage across this load, which is indicated by V of t. In the right figure, that is figure B, what we see here, we have a current source Is of t. It has its resistance across its terminals indicated by Rs, and then at the output terminal we are connecting a load RL, and we are asked to determine the current passing through the load indicated by I of t. Okay, so the question here is, what is that ideal condition of these two circuits A and B so that the voltage over here V of t will become equal to Vs of t, and in the right side of the figure B, we have to tell the ideal condition of this circuit in which this current, output current I of t, will become will be equal to the Is of t, that is the input current. So what we can do is that for the figure A, we have an answer here. So we can simply apply the voltage divider rule to this figure A. So in this way, expression can be written as, the output voltage can be written as V of t is equal to Vs of t and multiplied by this the ratio of these resistances, that is RL divided by RL plus RS. So if we have to make sure that these two voltages, output voltage equals to input voltage in this case, so what we have to see here, we have to have RS is equal to 0. If the RS is equal to 0 here, so there in that case we can have the output voltage equals to input voltage. Okay, as you can see here, the current can be represented by, output current can be represented in terms of input current multiplied by the ratio of these resistors. And if we want to have the output current be equal to the input current, what we need to have here, the resistance Rs has to be infinity. So again, if we have this ideal condition like we explained in the previous slide, like we explained here, if Rs is infinity, so in that ideal condition we can have that output current equals to input current. But usually that doesn't happen, so we don't have Rs is equal to 0 in the case of voltage signal, and we don't have a Rs is equal to infinity in the case of current source, because we have a practical limitations. So the design approach should be in such a way that in the case of voltage source, Rs has to be very less than RL. Okay, and in the case of current signal source, Rs has to be very greater than RL in this case. So in that case we can say that VO of t would be approximately equal to Vs of t, and here we will have IO of t, output current, would be approximately equal to Is of t. Is of t. So that should be the designing condition if we want to match these two currents in terms of current source, and we have to match these two voltages in terms of voltage source. So to the left side of this figure, we have to determine the open circuit voltage right over here. So there is this voltage source. The voltage source is given by Vs of t. It has a resistance Rs, and we are asked what is the voltage, open circuit voltage, indicated by VOC of t. So we can see that across these two terminals, it's simply this voltage, output voltage equals input voltage. Okay, and in terms of the current source right over here, we have this input current source Is of t. It has a parallel resistance across its terminal indicated by Rs, and the open circuit voltage in this case, voltage would be simply the multiplication of the current into resistance, input current into a resistance. What if we are asked to calculate the short circuit current? So again, we have this voltage source over here, we have its resistance, and we short these two terminals right over here, as we can see that. So in that case, the short circuit current right over here is indicated by ISC, short circuit current, as a function of time. And in that situation, current will be a voltage divided by the resistance, input voltage divided by its resistance. For the current signal source, if we short the output terminal of a practical current source right over here, and then we are asked to determine the output short circuit current, so it's like we are shorting the two resistance of this terminal. So in that case, the output current, which is a short circuit current, that equals to the input current over here. Okay, another example, it says that if the open circuit voltage is 10 millivolt, short circuit current is 1 milliampere. So it's just above this question, we have just seen what the concept of open circuit voltage and the short circuit current. So now if we are given the open circuit voltage to be 10 millivolt and the short circuit of a signal source is 1 milliampere, so what is the source resistance of that particular signal source? Okay, so source resistance, again we can apply the previous concept, Ohm's law. Ohm's law states, and we know that this is the expression we have, Vs of t, which is voltage source, can be represented in terms of current source Is of t into a resistance. So Rs would be simply the ratio of voltage divided by current, and that's how we can calculate the value of the sources. So this signal source will have a source resistance of 10 ohm.